Modification of clays and application in arsenic and fluoride removal. It has been observed that raw clays exhibit low adsorption capacities toward arsenic and fluoride adsorption from solutions. This is attributed to the permanent negative charges on the edges of clay sheets. As such, clay modification by higher density charged species and organic cationic surfactant is essential to improve their binding affinity. Common techniques that are used for modification of clays for arsenic and fluoride removal includes intercalation, coating and pillaring. Intercalation includes insertion of guest species in the interlayers of the clay mineral with preservation of the clay layered structure. Guest species may be the inorganic cations such as Mn2+, Fe3+, and Al3+, or organic cationic surfactants such as Ima and Cab. Jatari et al. Intercalated Fe3+ ions onto South African bentonite clay. Their results showed that the process involved the cation exchange between main exchangeable cations such as Mg2+, Na+, Ka2+, and K+. This was confirmed by the subsequent decrease of the content of these chemical species in the Fe3+ modified bentonite. Mujilwana et al. And Masindi et al. Intercalated Mn2+ and Al3+ onto the interlayers of bentonite respectively, and also observed decrease in the content of Mg, Na, Ca and K oxides. These results confirm that during intercalation basic exchangeable cations in the interlayers are exchanged for guest species. Pillaring is the most commonly used procedure to transform phyllosilicate materials into microporous and mesoporous materials. It involves the formation, intercalation and subsequent fixation of polynuclear cations between the clay interlayers. Thus the lamellar spacing and specific area increases, making these materials attractive adsorbents for adsorption of various inorganic contaminants. Presents a schematic diagram of a pillared clay. Schematic diagram of a pillared clay. Lenoble et al. Pillared Montmorillonite clay using titanium, iron and aluminum as pillaring solution. Their results confirmed that pillaring increases the basal spacing and the specific surface area by many folds. These results were confirmed by Mishra and Mahato, who also observed increased in both specific surface area for Mn and Fe pillared bentonite clay. Beside the change in basal spacing and chemical oxide content in the pillared clays, the whole process of pillaring does not change the mineralogical composition of the clay. Mishra and Mahato evaluated the effectiveness of Fe and Mn pillared bentonite clay in SV and S3, removal from groundwater. Maximum S3, and SV adsorption capacities of 17.57 and 25.77 G/G were observed for Fe pillared bentonite, while adsorption capacities of 25.77 and 26.17 G/G were observed for Mn pillared bentonite clay. This was higher by many folds compared to 4.31 and 4.33 G/G for raw bentonite clay. This was attributed to increased surface area in the pillared bentonite and also increased charge density in the pillared clay. Rin et al. Intercalated Fe polycations and cetyltrimethylmonium bromide, CMOB, onto Montmorillonite clay mineral and tested for arsenic removal. The results showed that CMOB had diffused into the interlayers of the Montmorillonite minerals while Fe polycations were adsorbed on the outer surface and had formed flocculent particles. When tested for arsenic removal, CMOB Fe Montmorillonite and Fe Montmorillonite showed a maximum adsorption capacities of 8.85 and 15.15 mg/G for SV, respectively, and 13.89 and 16.13 mg/G for S3. Furthermore, the optimum adsorption capacities were observed at wide range of pH of 4 to 10. Several studies have been reported concerning the adsorption of fluoride using chemically modified clay minerals, and the results showed improved adsorption efficiency as compared to unmodified clay soils. Campbell et al. Reported better sorption capacity for La, Mn and Mg oxides incorporated bentonite clay compared to bare bentonite. Efficiency of magnesium incorporated bentonite and adsorption of fluoride has also been evaluated by Takre et al. And maximum adsorption capacity of 2.26 mg/G was achieved over a wide range of pH, which was better than the capacity achieved with unmodified bentonite. Jatari et al. Reported maximum adsorption capacity of 2.91 mg/G for the Fe3+ modified bentonite clay, which was also better than the unmodified bentonite. The main factor which was leading to improved sorption fluoride capacity was the increased surface area that corresponds to availability of more active sites for fluoride ion adsorption. Furthermore, modification of clay mineral my high-density charges polycations increases the amount of positive charges in the surface of adsorbent leading to increased sorption capacity of anions. Table 2 summarizes the comparison between raw and modified clay soils toward fluoride and arsenic adsorption from water. It is observed that the adsorption of fluoride and arsenic increases by many-fold after clay modification. Comparison of the adsorption capacity between raw and modified clay toward arsenic and fluoride. NB, minus, equals not reported.